So hi, thank you for coming. I'm Francisco Fernández. Here you have my Twitter handle if you want to ask me something during the talk or whatever. Also, you have some questions during the talk, don't doubt about interrupting me. So, okay, let's start. Today I'm going to talk about garbage collection on Python. Here we have the agenda of this today talk. In first place, I'll do an introduction that includes the motivation, why I think this talk could be interesting for a Python developer, some known problems, some manual memory management, some definitions on garbage collection from academia that I think is also quite interesting to know about. And also every solution has some trade-offs, so we will explore them. Later on, we will see how CPython implements garbage collection. We need to know something a little bit about the C implementation, so there will be a little bit about C, all good C. Then I'll explain the algorithm itself, and finally the cycle detector. And if I have enough time, I'll try to do a high overview of how PyPy approach garbage collection. So let's start. Okay, what's the motivation on knowing more about garbage collection or memory management? We don't need to take care most of the time about memory in Python, and we are some kind of lucky. Most of the time we are working on a business logic layer because probably most of us, we are developers, not Python core developers, so we don't do native extensions. So we use a lot of abstractions that the language gives to us without knowing more. For example, we use a lot of dictionaries, and we don't know, we don't need to take care about how dictionaries are implemented or the layer between the operating system and the standard library. And also, memory is another abstraction that we have, and sometimes is useful to know about. So we'll know more today. I hope that you know more about how memory is managed in Python. Okay, but managing memory manually is hard. How many of you are familiar with C or C++? Please raise. So probably you know how difficult sometimes is managing memory manually. There is a lot of problems that I try to list here. Well, the most known is memory leaks. That basically is that we allocate memory for some resource, and after using it, we don't deallocate it. We do that most of the times by accident, no on purpose. Another problem that we have is the ownership. Let's say, for example, like in this snippet of code, this is some kind of library, and this library allocates memory on the heap, and it returns a pointer. Okay, everything fine. But who is responsible on freeing this resource? Who is the library should do? I do the free this resource. This leads to the problem of double freeze. What happens if I free the resource and again the library somehow had the pointer and finally tried to free? We end up with a segmentation fault in the best of the cases. Another problem that you can have is dangling pointers. For example, this is another snippet of code. We are allocating here a variable on the stack and returning the reference. And once we are out of the scope, this address is not valid anymore. So again, we will end up with strange behaviors. Segmentation fault will be the best of the cases because you know that something is wrong. Values that are not correct is the difficult one. Some languages propose some solutions, some patterns. For example, C++, they try to apply as much as possible write pattern. They also introduce some tools on a standard library like unique pointer and shared pointer. And also there are other approaches like in Rust that they try to make language safe on compile time. There's a lot of solutions. I don't know if in C you have much tools to deal with that. But we cannot have garbage collection in every scenario. There are some scenarios where it's mandatory to have full control of memory. One of them could be embedded systems where we have very limited resources and we need to carefully deal with memory. Also, for example, we have very demanding applications, like a video game can be, where, for example, we need to know very carefully how the memory layout is to try to avoid cache misses and so on. And also applications that need determinism, because most of the algorithms, as far as I know, on garbage collection, we don't know for sure when a resource is deallocated. So there are scenarios where garbage collection works and others than not. But what is all this about garbage collection? Probably most of you know what is, but I would like to introduce you a little bit about history. Here we have a picture of Mr. John McCarthy playing chess with a computer. And he was kind of the inventor of garbage collection. In this paper from the 1960s, the first mention to garbage collection on recursive function of symbolic expressions under computation by machine. And it's kind of funny because he described the whole process. He described mark and sweep algorithm there. And as a footnote, he says, OK, I've been naming this process garbage collection, but I know that academia is a bit picky, and I won't use. And finally, academia uses garbage collection, so kind of funny. So what's the formal definition of garbage collection? Garbage collection is basically automatic memory management. While the mutator runs, it routinely allocates memory from the heap. If more memory than available is needed, the collector reclaims unused memory and returns it to the heap. This sounds too formal, but it's quite simple. The mutator, you have there the definition, but basically it's our business logic. Nothing else. The heap is where the memory is allocated. And the collector is the garbage collection algorithm itself. In our case, Python virtual machine is the one that takes care about collecting unused resources. If you want to dig deeper into this topic, more in the academic side, this is a quite good book. It's quite extensive, but it's not so formal. So I recommend you to take a look. But as I told you before, every solution has some trade-offs. Nothing is perfect. So if we decide we are a language implementators and we decide to have a garbage collector language, we have to know that probably we'll need more resources. We will have performance impacts because the algorithm has to run. So we are losing CPU cycles there. And on some algorithms, we don't know for sure when resources will be free. Okay? So now we will start looking into how CPython implements garbage collection. It implements a reference counting algorithm, okay? But before, we need to know a little bit about how it's implemented in C. This is the main object that is exposed mostly for us as a user all the time. This is a Py object that is basically a struct with two members. One of them is Py size t that basically is for us an integer, name of ref count. Okay? This member holds the number of incoming references that an object has. So for example, if this is an instance B, and object A has a reference to B, the counter is 1, because it has one incoming reference. And the other member is just a pointer to the type. This allows us to have dynamic typing, okay? So let's see a simple example. For the purpose of this talk, that I want to be educational, we will only take care about instances. We know that foo class is also an object, but for simplifying, we only deal with instances, okay? So how does this look graphically? Okay, main is the main module, and it holds two references, one for foo, another one for my list. So those counters that I told you before are both 1, okay? Because only main is referencing foo and my list. But let's make this more interesting. Let's append foo to my list. Now, foo will have two references. We can see graphically like this, okay? Now foo has both main and also my list, referencing him. So that's happened. But who takes care about this counter? Presumably it's the CPython implementation. So here we have a snippet of the standard library on list object. This function, what it does is, given the list self, it appends the object v, in our case, foo, on my list, okay? And take a look into this line, py_inref on v. This is the point where we are incrementing by 1 the counter, because now the list self, in this case, has a reference to v, okay? And in this line, it sets in the last position the element. And how does this py_inref looks like? Like in a lot of places in CPython is a ugly macro. Basically, what it does is it does a cast on OP and increment by 1 the ref count. Easy. But what happens when an object is not referentiated by another one anymore? Well, presumably the counter will be decremented by 1. So we end up with this case in the same picture as before, because now my list on index 0 that before had foo inside now has none. So now we end up again with the same picture, because my list is not holding a reference to foo anymore. Okay, so foo again has a ref count of 1. And how does it look like on CPython level? Again, this is part of the listObject.c file that implements the list on CPython. And, well, again, we have very much like the inverse operation in ref on the old item that basically is the one that we are not interested anymore. What happens there in that macro? Basically, the counter is decremented by 1, but it also happens one check there. If this counter is equal to 0, we know for sure that no other element, no other object in the system running is interested in that object anymore, so we can safely dealloc that object. This is what happened here. It does the check here. If there is greater than 0, okay, does some checks. Other case, it deallocated. Okay, it's clear till now. Okay. And well, let's reproduce this case in our little example. Now we say to the module, okay, I'm not interested in foo anymore. Delete all the references there. Okay. So ref count reaches value 0, so we deallocate it. Well, the garbage collector, okay? And the interesting thing is that once we know for sure that no other object references foo, we can deallocate. We don't need to wait till collection like in other algorithms, okay? Collection phase. But do you notice any problem that this approach can have? Any clue? Probably most of you know what happens. But cycles. What happens with cycles? This approach don't work for cycles, okay? Like this. Now, let's imagine that foo has a reference to list, and we create a cycle. Foo has a reference to my list, and my list to foo, like this. Okay, now both objects live in main module, so no problem, they are there. No. But what happens if we don't take care anymore about foo on my list? We end up with a cycle, and those objects are not deallocated because both objects has a reference count of 1, and it's not possible that any one referentiate again because we don't have reference on our system. We delete from the module main, so we end up with a memory leak. And I told you before that one of the problems with manual memory management is memory leaks, and we also have here memory leaks. So what's the pro of having garbage collection? Well, we are lucky, and in CPython implementation, they implemented a cycle detector. Well, this is another topology that we can have, more complex cycles. Those are very, very simple examples, but in the real world, they are more complex. But yeah, what happens if we have a cycle? We'll explore how CPython implements the algorithm to check if there is cycles. To do that, garbage collectors should know more or less all the objects that are allocated on the runtime, and this is keep track on this double linked list. This is a node of a double linked list that lives in GC module with this signature. And for performance reasons, there are 3 generations on the implementation, because doing a whole scan or looking for cycles on the all living objects is quite costly. So what they do is they divide into three generations, from the youngest one to the oldest ones, and we do step by step. So we don't need to check for the whole living objects. Okay, and well, this is some C tricks to. This is a union. Well, don't worry about it. It's just some details. So let's represent our example like the one before. We have those 3 generations, and we have foo and mylist. Both of them, probably you can see in the back, but both of them has the value 1 on GC refs. And what's the key idea of the cycle detection algorithm on CPython? The key idea is that we know the object that belongs to a generation. So what we can do is extract all the internal references on that generation, and those objects with a number of references bigger than 0, they have references from other generation objects. I don't know if I explain bad or, but the idea is that we keep track only on, we subtract all the internal references in the same generation. I'll do step by step, trying to explain better. To do that, types internally on CPython implementation has this method that abstracts how to traverse all the references on an object. So for example, I implemented this as a Python to do it more clear. So for example, dict abstract traversing all the references basically as iterating over the key and value and applying some function. A list, basically iterate over all elements and apply a function. This is a utility that we have for this kind of problems like cycle detection. Okay, so those tools help to implement the algorithm. Okay. So let's start. Let's think that we only have foo and mylist on my generation 0. Okay, to simplify things as much as possible. So I start iterating over the first element, that in this case is the one marked in red, foo. And what I do is, using these functions, depending on the type, I iterate over all the references that this object has. Okay? In this case, it's only my list. And I apply one function. This function, what it does basically is check that the number of references is greater than 0 and decrement by 1. So with this way, we are breaking the cycles, okay? Because all the internal references are decremented. So if we have a case like this one, we are breaking it. We are marking as unreachable. So this is the first step. Foo only has a reference to my list, decrement by 1. Now the reference is 0, okay? The next step, we have my list as the next object in the generation 0. And again, we decrement by 1. So now we know that those objects could be unreachable outside of of my generation. Okay. The next step is moving those objects to a new list called unreachable. And one step that we have to take care is we need to check on objects that are reachable all the references, because there can be cases where some object get a value of 0, but there is some kind of topology like one cycle, like the one that we were seeing before, and two other references. These end up having 0 on those two objects, but they are still reachable by these two objects. So we have to check for that also. After that, we move to an unreachable list. Those objects that are reachable are moved to the next generation because they can live more. But I prepared like a little demo written in Python. Before I did this using GDB, but it was too much. So let's take a look. I have time, I think. Can you see the code over there? Yeah. Well, I tried to represent like more or less the implementation on Python to make it easier to understand. Do you remember this double linked list? This is one of the represent the nodes on how the garbage collector tracks all the allocated objects. Okay. These are some helper methods that implement the traversal methods to know how to iterate over the references, one list. Some examples. We will run an example now, okay? And here we have the garbage collector object, okay? It has, in this case, 2 generations with 2 thresholds that I didn't mention before. But we don't do as cycle detection each time that we allocate an object. There is some threshold that they studied, and if we allocate more objects than that threshold, and cycle detection is fired. Okay. Here we have this logic. Let's say that I want to instantiate some class. What I do is I append to my first generation this object on this linked list, and I check this threshold. Okay, is my generation greater than the threshold? Yes. I collect. I do a collection. How is this collect cycle? Okay, we get some references for being more comfortable programming. The first step is we need to update the references, because on the nodes, this node don't have the most updated reference count, because as I told you before, we don't run the cycle detection all the time, so it can have a value that is older. Okay, so the first step is we iterate over all the generation that we are interested in, and we update the reference count with the pi object 1. Okay? The next step is this one of breaking cycles, just subtracting 1 on the internal references. Okay, so let's take a look how this. What we do is, again, we iterate over the whole list of this generation, and using this helper method that abstracts how to iterate over all the references, we pass a function as an argument, okay? And this function, basically, what it does is it checks that the references are greater than 0 and decrement by 1. This is a helper method, so don't worry about it. So we end up with the, after this step, I will run one example. Oops. Do you know how to evaluate all the cells on EuroPython? Okay. I'm pretty new to notebooks. Sorry. Okay. We'll do like a step by step to see it clearer. Okay. We allocate one list. We are trying to replicate our sample. We have a list and an instance of an object, and we are creating a cycle. Okay. We allocate. I don't know. We'll explore line manually. I don't know what's happening. Demo. Effecto demo. Okay. After this step on our example, we will get those two objects with a count of 0. So the next step is just check those edge cases where we can get some object with a count of 0, but some other object can referentiate them. So what we do is, in first place, we use again TP traverse, and we use another callback. That basically what it does is, if we find one object that has a count 0, this is a false positive as unreachable, so we need to keep track that he's still reachable. In our case, we just check that refs are greater than 0. And after that, we have those two lists, the unreachable object and the young ones. So we know that these ones can be deleted. But it's not so simple. So we move the reachable objects in this generation to the older one. And I'll explain later what we need to do with weak references and finalizers. And we finally delete all the garbage. There are some edge cases that I'll try to explain now. But did you understand more or less the algorithm? Should I explain something more, or is clear? Okay. But as I told you before, there are some problems with this approach. We need to take care about finalizers. I mean, underscore deal. There are two kinds of finalizers. Ones are kind of legacy, and those cannot be deallocated safely, so we end up having memory leaks if we have legacy finalizers. With underscore deal, it also has to take care a lot of edge cases, so please don't use finalizers. And finally, we have to take care also about weak references. What it does is check the ones that are reachable and execute the callback that they have associated. So what makes the emoji happy? That is incremental. This algorithm is incremental, so as it works, it frees memory. We don't need to wait to a cycle to recover memory. And emoji is worried because, as you can see, detecting cycles is kind of hard. Not the algorithm itself, but there is a lot of edge cases that I didn't mention, but it's kind of complex. And we also have some size overhead on objects that this OV ref count. And as a personal opinion, also in CPython, garbage collection is too coupled to the model, so that we have a counter in the main object of the interpreter. So it's not so we cannot change the model easily. So that's as a side note. And I have little time now, like 5 minutes. I'll try to do an overview of how PyPy handle garbage collection and memory. So probably most of you are familiar with PyPy. It's an alternative implementation of Python. It's written in EuroPython. And regarding to garbage collection, it has some points that are quite interesting. One is that it's kind of agnostic to the garbage collection algorithm. So during translation time, that is how do you get the interpreter at the end. You can, if I'm not wrong, you can change the model of garbage collection, the algorithm that you want to use. So this allows PyPy developers to experiment over time with different approaches that I think is a good good thing, not to be tied to one implementation. And the algorithm by default nowadays is in Minimac. And let's explore a little bit about PyPy. One of the things that PyPy developers notice is that we allocate interpreter allocate a lot of objects with a short lifetime. So, for example, we have some examples here, like for comprehension, we are allocating objects that will live very, very shortly. Even when we are calling a method on a class, we are creating a new object, a bounded method, with a very, very short life. So those objects will be allocated in a performant way. Okay? So they end up with this kind of memory model. They divide it into two areas. One for the John objects, this one that lives shortly, and the John area is divided into two areas. The nursery that has a fixed size, another area where all the objects that don't fit in the raw malloc area go there, and also some arenas to hold the objects that are older than the John ones. Sorry. So how does it work? It performs what they call minor and major collection. Minor collection is performed on the John area. So it's fast because we don't need to transfer to the all live objects, and objects are moved only once to the old area. And also major collection is done incrementally. At the end, they implement kind of a mark and sweep algorithm that, well, these are the phases that they implemented. In the first place, they do a scan phase, then mark, they sweep, and finally they execute finalizer because we have the same problems as in CPython. Here we have some schema of how mark and sweep works. In general, this is it's the same schema as in the paper of McCarthy. Basically, what we do, we know for sure the root of the main objects, and we traverse the graph of memory, and we mark on this traversal which ones are reachable. Once we know which ones are reachable, we iterate over the whole list, and we sweep, we allocate the ones that were not marked. And yeah, that's it. Quite simple and elegant. Mark and sweep can collect cycles because we basically are doing a graph traversal. But PyPy implementation can be more complex to understand than CPython because, yeah, at least for me. And on full collection, we stop the work. I mean that we cannot, as well as when we are detecting cycles on CPython, we cannot perform other operations. So, yeah, questions?
Start up front if there are any. There are a few at the back.
Hi, thanks for the explanation of these algorithms. What I would be interested in as a Python developer, is there anything I should take care about in my code so that I enable the garbage collector to do his work most efficiently?
I'll try to avoid underscore deal methods, for example, because there are a lot of edge cases that the interpreter has to take care of. So that's one of.
With PyPy, you say there is a possibility of the stop the world issue on garbage collection. Is there a way to, in future implementation or theoretically, to circumvent this circumstance? For example, splitting memory and garbage collecting different.
Yeah, they do that approach. So the stops, as far as I know, they're not so long. So, but it could be interesting having like in the JVM, where you have parallel strategies and so on. That will be interesting.
What about threads?
You cannot have parallel code running because the global interpreter lock, as far as I know. But I don't get your question. Can you elaborate more? Or?
If I run more than one thread, then each thread allocates, and then it has to be garbage collected. Is the garbage collector specific per thread, or is it global to all the threads?
It's global, as far as I know, on CPython. On PyPy, I'm not sure.
Can you force the garbage collector to run, or is it free also to ignore it if you can, if you call it?
Can you repeat the question? I didn't hear you well.
Can you force the garbage collector to run, and if it does, is it free to ignore it?
That you can force a cycle on GC module. At least on CPython, you can import GC, and you can force a collection, a cycle detection, because on reference counting, resources are free when they are not used anymore. You can force a cycle detection. Yeah. But you have an API to manage garbage collector.
Could an object be resurrected by its finalizer?
I didn't hear you. Can you repeat the question?
Can an object be resurrected by its finalizer?
Yeah. That's one of the edge cases that you have to handle. Yeah. That's why it's not good practice to.
Is the garbage collector the one that collects cycles gathering any statistics? Can I inspect and see some statistics?
Yeah, you have through this API on GC module, you can check, as far as I can remember, number of reachable objects. Let me check. Well, you have over here documented somewhere, but it check for statistics all the time. So importing GC, you can access to some of them. Yeah, definitely. Oh, yeah.
So does it run with a certain frequency, or how often, or?
On CPython, it depends on this threshold. So each time that an object is allocated, is appended to the youngest generation list. And once we reach this threshold, a cycle detection cycle algorithm is done.
Last question. We don't have time for more.
Do you know about some user-friendly tools to detect memory leaks before you deploy your application?
I think there are some, but I don't know. On the worst case, you can use Valgrind, but not so user-friendly. And you have to know the internals. So. But probably there are some that I'm not aware of. Sorry.
Great presentation. Thank you very much, everyone. Please.